Good day, guys. Alright, so in this video what I want to do is to talk about thin films, specifically thin film interference. We have looked at interference before in the young double slit experiment video. Alright, so now we will look at another example of interference before going into diffraction next in the next video. Alright, so let's look at thin films. Now, one of the key concept that you have to know is that in thin films interference, another focus is this idea called phase change upon reflection, and this is very much keen into the wave property of light, right? So let's say we have a surface, right? An object with a surface, right? And you have an incoming wave that is illuminated onto the surface of the object, and then it's reflected off, right? Now, whether or not that outgoing wave is going to have the same or shifted, right, or phase changed compared to the incoming wave depends on the refractive index of the initial media, which is N1, and the refractive index of the second media, which is N2. So if N2 is smaller than N1, then the wave will experience no phase change. Okay? Now, however, if N1 is smaller than N2, right, N1 is smaller than N2, then the wave will experience a phase change. Okay, so how does that help me in understanding thin films interference? Well, we can start with a diagram. So let's just assume that this is air for now. Okay, I have a refractive index of air, and I have an incoming light wave or incoming light. And then at that air coating interface, you will have a proportion of it, a portion of the light to be reflected off, right? And then some portion of it being transmitted. Okay? And then again, this light is again reflected off of the coating object interface and then is transmitted back into the air. So I have two reflections occurring, and I have to ask myself at least, whether or not there were phase changes, right? So let's look into it. Air has a lower refractive index than coating, so you will experience phase change for the first um, light reflection. For the second one, if the object has a higher refractive index than coating, then here we will again have a phase change. Okay, so then our phase difference, right, is only going to be depending on the thickness and refractive index of the coating, which is 2 multiplied by n coating times t. For constructive, right, for constructive interference, then we'll need this 2nt to be equal to m lambda constructive. Okay, now of course for destructive interference, what all we need to do is just add that order by half, right? M plus half lambda. Okay, now let's now look at the opposing case. If the refractive index of the coating is higher than the object, then we will experience phase change for the first one, and no phase change for the second one. No phase change. Okay, again, because the refractive index of air is lower than the refractive index of the coating, so phase change here, yes. However, because the object has a lower refractive index than the coating, then no phase change here. So then what we're left with is this phase difference between the two waves, right, to be 2nt. Again, this 2nt comes from the fact that light traveled to and fro, right? And then minus, I'll use minus half a lambda. Okay. Again, at this point, we want to use for constructive interference. We want to look for the equation for constructive interference. I'll equate that to nt minus half lambda to m lambda because that's the condition, right? So what I'm left with is 2, the refractive index of the coating times t equals to m plus half lambda. Okay, so two very different equations from two very different cases. Okay, all right. So now what we can do is you can attempt to apply that to a work example, right? So here's a work example. This is from the examination PSPM 1819 for the the Malaysian matriculation examinations. So the question goes, calculate the thickness of a soap film. So soap film meaning that we have air and then soap and then back to air, so that a 600 nanometer light incident to the film would produce a constructive interference. Index of refraction force of soap film is 1.33. For now, I'll use air to be 1.00, 1.00, right? So I have a incoming light reflected off, then coming back in, transmitting through the soap, and then coming back out through the air. Okay, so now what I have is two reflection. Is there a phase change for the first reflection? Yes, there will be going to be a phase change on the first reflection. Is there going to be a phase change on the second? No, there will be not. So what I'm left with is 2nt equals to m plus half lambda. Okay, and this is for the constructive interference. Okay, right. So because we would assume that we're talking about minimum thickness. This is an assumption, right? Then I can have m equals to 0. What I'm left with is t equals to half a lambda over 2 n being the refractive index of the coating, right? So what I'm left with is half times 600 nanometers. So 600 nanometers is -9. Then I have to multiply by the refractive index of the coating, which is 1.33, right? And that gives me a value of approximately 112.8 nanometers. Okay, so that's how I calculate that. And that's also through this diagram, I can work out the equation for constructive interference for this particular case. Obviously, this is going to be very different for other cases as well. But as long as you remember that you need to look for phase change upon reflection and the conditions for constructive interference, then you should be fine with solving any thin film problem. All right. Okay. So that is all from me today. Thank you very much. I'll see you in the next video.